Okay, we're going to start now with section 1.3, properties and vocabulary for arithmetic calculations. So our objectives in this section are to identify and use the commutative property in calculations, use the associative property to evaluate arithmetic expressions or arithmetic expressions, use the order of operations convention to evaluate arithmetic expressions or arithmetic expressions, identify and use the properties of exponents in calculations, and convert numbers to and from scientific notation. Does anyone have any questions so far? Okay. So, we're going to talk about some definitions, so terminology. The four operations of arithmetic are addition, subtraction, multiplication, and division are called binary operations because they are all ways for combining two numbers at a time. So bi means two, so binary means combining two numbers at a time. Now, when two numbers are added, the numbers are called terms, and the result is called the, I'm going to let somebody else answer this one other than me. What is it called when we add two numbers together? The sum. The sum. It is called addition, but what we get when we add those two together is called a sum. So when two numbers are subtracted, on the other hand, the numbers are also called terms, and the result is called the difference. Difference. Oops. So, when we have addition, the result is a sum. And when we have subtraction, the result is a difference. Very good. Okay, now we're going to move to multiplication. So when two numbers are multiplied, the numbers are called not terms anymore. They're called, starts with an F, factors. I have to be careful anytime we start with a word that begins with an F. And the result of multiplication is called a P. Product. It's a product. I'm sorry, what? Was there a question?
I wrote my F backwards.
Oh. What does that look like? It looked perfectly normal to me. I hope you can appreciate that if it was backwards to you, it would be right side to me. So when two numbers are divided, the number being divided is called the dividend. The number it is being divided by is called the divisor. And the result, let me rewrite it. Oh, you're good. Is the dividend, D-I-V-I-D-E-N-D, dividend. Yes, divisor is the second word. The number it's being divided by is called the divisor, and the result is called the, you're close. It does start with a Q. Quotient. Wow, it's so quiet in here without the air conditioner on.
It psyched me out because I picked the same time my Adderall did.
So this is the moment. This is the moment you're locked in. do need to pass around the sign-in sheet. So your name should be listed on the left-hand side, the right-hand side. If you'll just sign it, make sure you sign in before class is over. Does anyone have any questions so far? So we've talked about how many operations? 4. And what are they? We have addition and the results of those in order are sum, difference, product, quotient. Very good. Man, y'all are on it today, even at 8 o'clock in the morning. I'm proud of you. Okay, the commutative property of addition. So when the order in which two numbers are added is reversed, the sum remains the same. In other words, we can add numbers together in any order we want to. You can change the order, doesn't change a thing. This property is called the commutative property of addition. And it can be written symbolically as A plus B is equal to what? B plus A. In other words, we can change the order in any way we want to, and it doesn't change the result. Now, what is that result called?
Sum.
It's a sum. Okay, just checking, making sure we're on the same page. So, do you believe that 5 plus 13 is equal to 13 plus 5?
Yes.
Why do you believe that?
Because it's 5 plus 13 equals 13 plus 5. You add the 5 plus 13, you get the same amount.
Well, what is the result?
The sum is the same.
What is the sum in this specific case? 5 plus 13.
Oh, my bad.
18.
They're both equal to 18, right? Are you sure it's kicked in?
Yeah.
So, because the result is the same, we know those are equal, right? And so any combination of addition, you can change the order. That's a big deal, okay? That's not true for just every operation. It is true, however, for multiplication. So the commutative property of multiplication says that when we have two numbers that are factors and we reverse their order for multiplication, the product is the same. Symbolically, again, commutative property of multiplication. Symbolically, that's written as A times B is equal to what? B times A. The one I always like to use is 2 times 3. What's 2 times 3?
6.
What is 3 times 2?
6.
6. So if someone asks you, like, I don't know, me, if your math teacher asks you, what is the thing that says that we can change the order of multiplication, that we can reverse it and get the same result? What's that called?
It's called commutative property.
It's the commutative property of multiplication.
Multiplication, yeah.
Now, there is a commutative property of addition, and it's right here. It says that we can change the order of addition without changing the result. It is a very fancy way of saying just that. Yes. Any questions about the commutative properties?
Well, the only thing between addition and multiplication, you said in order two numbers factor or multiply in reverse, but they're factors. In the commutative property is proper.
Has everyone signed in? Oh, has it gone to the right side at all? Thank you.
Well, okay, you are today.
Okay, the next one, the associative property of addition. So the associative property of addition says that we can regroup addition in any way that we want to. So we can put parentheses around things and group them in different orders. In other words, if I have sum sum, if you will. If I have A plus B, that quantity, then we add C, I can change the way that I associate those. I can do the addition in a different order. In other words, something like A plus B plus C. So I can regroup them using parentheses. So I want you to note that the parentheses are symbols used to group numbers. The operations that we have within parentheses, we always do those first. Why do we do that first? It could change the outcome. In this case, we see that it does not. Why do we do the operations in parentheses first? No. Let's think big picture. Think about order of operations. Does anyone know order of operations?
Yes, that P-E-N-D-A-S.
Yes, and what does the P stand for? Parentheses. So grouping symbols. We always do those first. Has everyone signed in now? Yes, no, maybe? Okay. I'm going to mute my mic for a second.
We did the same thing.
And we're back. Okay, the associative property of multiplication. Very similar. So symbolically, we can write that as the quantity A times B times C. We can regroup that as A times the quantity B times C. Again, the way that works is that we would multiply these two together, the A times B, and then multiply it by C. In this side, we would multiply the B times C together and then multiply by A. And it turns out that the result of those is the same. So that's the associative property of addition and multiplication. Does anyone have any questions so far?
P-A right here.
There you go. Here's a little note for you. This is probably the only time that anything English or grammar will come up in this entire class. So parentheses are plural. So you can't have one parenthesis, okay? They come in pairs. So if you have two of them, that's parentheses. If you have one, does anyone know what it's called? So if you have a pair, those are a pair of parentheses. What if you just had one? You always go back to that, don't you?
That was a good joke.
It's a parenthesis. Oops, I can't even spell it. Parenthesis. Yeah. Is anyone ever going to expect that you'll know that? No. You'll
Does that ever come up in just like one of those problems where it's just one?
No.
Probably.
Not generally. Now, generally, they'll come in pairs because it really doesn't make sense to... You can't group things if you only have one. Like, they could escape if there was only one. It's a good question, though. Okay. Using the associative property. Explain how you might reorder and regroup the factors 2, 4, 5, 6 to perform the calculation in your head easily and quickly.
Parentheses.
Yes. Yes, parentheses would help us do that.
2 and 4 and 5 and 6.
Yes, but is there a faster way?
2 times 4, parentheses, times 5.
Okay.
I think.
Let's zoom out for a second. What things are easy for us to multiply?
The 2 times 4.
Remember, we have the commutative property. We can change the order too. You don't have to do 2 times 4. You could change this and make it 2 times 5. And you could do 2 times 6. Which things are easiest for us to multiply? 5s and 10s, right? 5s and 10s make things much easier for us to multiply. So, what if I use the commutative property and I change the order to 2 times 5 times 4, times 6? What do we think about that? But not just that. I'm not done. Now I'm going to use parentheses and regroup, and I'm going to consider those two things separately. What's 2 times 5?
10.
And what's 4 times 6?
24.
24. 10 times 24? 240. Now, if you had done 2 times 4 first, it would have been harder, right? You couldn't have just done that easily in your head. So you want to reorder it in a way. Now, you don't have to reorder it ever, right? You could have gone through and plugged this into your calculator. Boom, 240. But if you're trying to do it in your head and do it quickly, group to make it easier, you want to use things that you know the multiplication tables of. And you know that when you multiply by 10, you basically just add a 0, right?
Right.
Okay, so words. So I multiplied 2 and 5 to get 10. Then, I'm going to scroll up, I multiplied 4 and 6 to get what? 24? Finally, I multiplied 10 and 24 to get 240 because that meant adding, let's not say adding, let's say appending a 0 to the 24. Now, there's a difference between adding and appending, right? So if we were adding a 0, that really would go in the face of what we've been doing today. So adding a 0 would just give us the same thing. Does anyone have any questions about how we use that for simplifying with using mental math? Okay. So our next example, we want to evaluate 2 times the quantity 3 plus 4 times 5 and classify this expression as a sum, difference, product, or quotient. Number 1, you can't classify it from the first step. We'll classify it at the last step. So, what do we do first?
You want the parentheses first.
We do the stuff inside the parentheses first, right? Okay. So first, evaluate the arithmetic expression in parentheses using what? What was that?
You're gonna have 7.
We're going to use order of operations, right?
3 plus 4 equals 7 times 5 makes 35. Do you want to?
So the first thing we do is what?
You're gonna add 3 plus 4.
No, we're
You're
not.
wrong.
No, we're not going to add 3 plus 4 first.
We're gonna multiply.
We're going to multiply first. So multiplication
yeah,
always
yeah.
comes before addition and subtraction. So that is, we multiply 4 times 5 and then
Okay.
add 3. Okay, so that gives us what? What's 4 times 5? 20.
Plus 20. In the
So
parentheses.
3 plus 20. Okay, and now we add that 3 and 20 together.
3.
23. So 2 times 3, 23 is 46. What was the last operation we did?
Multiply.
So that means this expression is a...
That means it is a product.
It is. The expression is a product. That's all. Does anyone have any questions?
Right.
You're good. Take your time. Okay, are we good to move on? Okay. Oh, I wrote the whole word down and product was... That's embarrassing. And on today of all days. Okay, exponential expressions. So exponents and exponential notation are really useful for us in simplifying an expression that has repeated multiplication, such as 3 times 3 or 5 times 5 times 5 times 5. When we have the first case, 3 times 3, how many times are we repeating that 3? We're repeating it twice. So that repeated factor is called the base, and the number of times that we repeat it is called the exponent. So if we have 3 times 3, that can be rewritten as 3 squared using exponential notation. You've probably seen that before. That's where we have our base raised to what power? Well, it's raised to our exponent power. In the second case, we have 5 times 5 times 5 times 5. How many factors is that? 4. And the product can be written as 5 to the 4th power. I always try and edit out my coughs if I'm recording. So if you do need to exclaim something, just tell me and I'll. So we need to edit that out, right? Any questions about exponential notation? Okay, let's talk about perfect squares. So a number is called a perfect square if it can be expressed as the square of a natural number. What are the natural numbers? No, the natural numbers are 1, 2, 3, 4, 5, and so on. Sort of makes sense because those are the numbers we count with, right? So they're natural numbers. So 100 is a perfect square. or 25 is a perfect square because 10 squared is 100 and 25 squared, or 25 is 5 squared. So let's do a little list. Do y'all have the box on yours? Okay, so what's 1 squared? 1. 2 squared?
4.
Yeah, that pattern doesn't repeat after the first one. 3 squared? 9. 4 squared? 16. 5 squared? 25. 6 squared? 36. 7 squared? 8 squared? 64. 9 squared is? And 10 squared? 100. So, these guys right here, and I picked up my pencil, so I'm going to have to write it again. These are perfect squares. Does anyone know what 11 squared is? $121. 12 squared is 144. What about 13 squared? $169.
14 squared is 196.
14 squared is 196. 15 squared is 225. That's about where my knowledge ends. 16 squared, I guess, is probably 256.
Yeah, it is.
17 squared, let's see, 289. Is that right?
Mm-hmm.
18 squared, I'm not even going to guess. 324, maybe?
Yes. Wait a minute, hold on a minute.
I can't do 19.
Wait a minute.
19
I'm finna do it
squared
for you, hold on a minute.
is between 324 and 400.
361.
361. And then 20 squared is 400. That one's easy because it's 2 times 2. But that's not why we're here for my poor memorization of perfect squares. So closely related to perfect squares is, to raising a number to the second power, is its inverse operation of taking the square root. So we use a radical sign to signify a square root. So if you take a square root of a perfect square, you get the number in the left-hand side of our table, right? So if you take the square root of 36, you get 6. If you take the square root of 64, you get 8. Your calculator will also do square roots. Basically any 4-function calculator. Well, scientific calculator. A 4-function calculator would only do 4 functions. Does anyone know what those 4 functions are on a 4-function calculator? That's it. So the radical sign is a grouping symbol. Underline that. The radical sign is a grouping symbol. So all of the operations inside the radical have to be performed first before you actually take the square root. That's very, very important. Now, we're officially to talking about order of operations. Does anyone have any comments, questions, concerns, criticisms? What ifs? Okay, order of operations. So we perform operations inside all grouping symbols first. What are the grouping symbols we've talked about so far? Grouping symbols. Parentheses, square roots, also expressions in a numerator of or a denominator of a fraction. that helps us group also. So we have numerator or denominator of a fraction, inside a radical, and within parentheses. Brackets, left and right hand brackets, also act as parentheses. So there's no difference between those. And then all operations we do are performed in the order that happens below. First, we evaluate all exponential expressions as you read the expression from left to right. That makes intuitive sense, left to right, because that's how we read in general, right? Okay. Then after we do all of the exponential expressions, then we move on to multiplication and division as you read the expression from left to right. Now, what if I have division that comes first, left to right? Do I do multiplication first or do I do the division? I would do the division first because we do it from left to right. So if we're looking at all the multiplication and division together, if division comes first, you do the division. If multiplication comes first, you do the multiplication. So again, we do it as you read the expression from left to right. And then we do all the addition and subtraction the same way, from left to right. So if you have subtraction that comes before addition, that's perfectly fine. You do the subtraction first. So as you read the expression from left to right. So this is where you've probably heard PEMDAS, right? So if it's lined up in order, that's fine, but that almost has us treat them separately. The way I want you to think of it is, I want you to do all the P stuff first. Oops. Then all the E stuff. Then the MD stuff. Then the AS stuff. So how many different steps do we have? We have 1, 2, 3, 4. So why are there only 3 here? Well, because the whole first paragraph told us that that's where we do our grouping symbols, right? Don't worry, you're going to get plenty of practice on this. Probably more than you want from now until the end of the semester. We good? Okay. We want to evaluate the expression 20 minus 2 times 3 squared. I'm going to let you read over it for just a second, and then we'll talk about specifically what we do first. What?
You gonna multiply the 2 times 3. Well, 3 times 3 equals 2. It's only first. 2.
So, this is the way I approach all of these problems. I start by asking myself questions. And my first question is, are there any parentheses or grouping symbols?
No.
No, there are not any grouping symbols. Since there are not any grouping symbols, so there are none of those. So we then move on to the exponential expressions. So we evaluate all exponential expressions as you read the arithmetic expression from what? Left to right. Okay, so when we do that, what do we have in an exponent?
3 squared.
3 squared. And what is 3 squared?
6? No, 9. Yeah.
Yeah, 3 squared is 3 times 3. Okay, we've done all of our exponential expressions. Do you agree with that? Now, the question is, do we have any multiplication or division? We do have multiplication or division. What do we have?
9 times 2.
We have 9, negative 2 times 9.
Negative 2 times 9.
That matters. So, we're going to perform what? All multiplications and divisions as you read the expression in what order? From left to right. Now, in this particular case, we only have one multiplication, right? So we have negative 2 times 9, which is negative 18. So we have 20 minus 18. Do we have any more multiplication or division? So we're done with that. Do you see the methodical process I'm taking to go through each and every step of this order of operations? This is how you need to approach these problems. Because if you try and rush through it, you'll get out of order and you'll make a mistake. So, we now have addition and subtraction. Do we have any operations involving addition or subtraction? Yes, we have subtraction, right? So we perform all additions and subtractions as you read the expression in what order?
Right.
From left to right. Now, am I going to write all of those things every time I do this? No, I'm not. I want you to see the framework of how you do order of operations. What's 20 minus 18? 2. So that's your result. And your result is it's a difference. That was the last thing we did. Does anyone have any questions about how we do order of operations? Bless you. Are you allergic to math? We started doing order of operations and the sneezes come out. Any other thoughts on this problem? Now's a good time for me to pause and ask you, how is our speed? Are we going at a good speed, too fast, too slow, or just right? Okay, I like going for that Goldilocks speed. I want to be right in there. Okay, scientific notation. You're going to see scientific notation the entire semester, so just be prepared for that. I want to spend a little time talking about how we deal with scientific notation. So a number written as the product of a decimal number between 1 and 10 and a power of 10 is said to be written in scientific notation. So, what does that mean? Well, the definition is we have a times 10 to the n, 10 to some power, where a is greater than or equal to 1, so 1 is included, and less than 10, meaning 10 is not included, and n is an integer. Barbie, you're looking at me with some consternation. So our scientific notation is just going to be a number between 1 and 10. Someone tell me a number between 1 and 10. 8. 8 would be perfectly fine. Pick another number. Okay, what about 6.345?
Yes.
That's between 1 and 10, right? What about 1? Is 1 included?
Yes.
Read. 1 is included.
But 10 is not.
10 is not included. So what does this tell us?
It's gotta be less than 10.
It's got to be strictly less than 10. That means at most, how many digits will you have to the left of a decimal?
9. What?
Okay,
Oh, to the left.
to the left of the decimal. What is the most number you could have left of the decimal? Try again.
8,
Try again.
6.
Try again.
No, it's gonna be negative. Right?
Okay, friends. Okay.
Oh, no.
So if you have something that looks like a number, doesn't matter what number it is, times 10 to some power, but we know that that number is greater than or equal to 1. Okay? You've told me examples. Let's talk about the examples you said. You said 8. You said 5.
You said
I said 6.345. Tell me some more. 7. We said 1 was included. 2 is included. Where is the decimal in each of these? It's right after the digit. How many digits are to the left of the decimal? 1.
Oh.
Gotcha.
Oh, okay.
Okay.
So is 10 included?
No.
No. Why not? There's 2 digits. So 10 is not included. So does that make sense? That if it's going to be in scientific notation, the only way it can be in scientific notation is if there is 1 digit to the left of the decimal.
Is that all problems? Just
For scientific notation, period. Now, that's not for all things that are not scientific notation, but if you're asked to do something with scientific notation, that number always has to be between 1 and 10. And that's what guarantees us that we won't have more than 1 digit to the left of the decimal. Yes. Okay. So let's start with an example. We want to write 9,420,000 in scientific notation. My first question when I deal with scientific notation is, are we dealing with a big number or a small number? And I think we can all agree that 9,420,000 of anything is a big number, right? What do you wish you had 9,420,000 of? So 9,420,000 pennies? What would that be?
Dollars. You want dollars.
You want dollars, right?
Yes.
You could get 9,420,000 pennies, though, right? That's a thing. Except we're not making pennies anymore, which is,
You better say the ones you got that are worth some money.
yeah, they're worth less than a penny. That's the problem. Nice. That probably is actually worth something.
$10.
What?
$10.
Oh, wow.
Yeah, put that toward your retirement.
I don't have 401k for that.
There you go. Okay, so the way we want to do scientific notation is we want to place a decimal point immediately to the right of the first digit. So 9.420000. Same number of digits, but remember, we want the first digit to be the one we care about, right?
Right.
I count 4, so 420000. Then we count the digits to the right of the decimal point. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. There's 6 digits, right? Yeah. 6 digits. And then we drop all the trailing digits in the trailing zeros in the decimal and multiply by 10 to what power? 6. So 9,420,000 is equal to 9.42 times 10 to the 6th power. Yes.
Where did we get 10 from?
So every time we move that decimal over a place, that's where we multiply by 10. Always. Because our numbers, the whole system of numbers we use, think about it. When we start counting up, start counting at 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. When do we add another digit? At 10. Okay? And then we go up to 20 and 30 and 40 and 50. When do we add the next digit? At 100, right? We don't add another digit to the end until we get to 100. And then we don't add another digit then until we get to 1,000. So it's every time we multiply by 10 that we add a digit. Is this making some sense? So another way to think of this is we know that when we start with 9,420,000, where is the decimal? It's right here, isn't it? Mm-hmm. If you move that to be in this position, you would have to move it 1, 2, 3, 4, 5, 6 times. And that's another way to do it. It's actually the way that I would prefer to do it, which is perfectly fine. In that case, though, if you decide to move the decimal, you need to know which direction you're moving so you know your power on 10. Because in this case, was it a big number or a small number? It's a big number. So we're multiplying by a positive value of 10. Well, they're all positive, but by a positive power of 10. In our next example, that's a really small number, right? 0.00, I've got to look closer on mine, 0.0003042 inches. That's not a lot of inches, right? It's not a tenth of an inch. If it were a tenth of an inch, that would show up here. It's not a hundredth. It's not a thousandth. It's 3/10,000ths of an inch in diameter. That's pretty small. So we want to write this in scientific notation. How many places do we need to move this decimal? 1, 2, 3, 4. Why do I only have to move it 4?
Because it's to the right of the first.
It needs to be to the right of the first digit. That guarantees that our first digit will be between 1 and 10. So we'll have 3.042 times 10 to what power?
To the 4th power.
To the negative 4th power.
Oh, because they're going. Okay.
So when we're moving the decimal to the right, it's going to be negative because it's a really small number. And I try not to remember right and left. I try and remember, is it a small number or a big number? If it's a big number, it's going to be a positive exponent. If it's a really small number like this, it's going to be a negative exponent.
Explain to me, you said the first time you asked a question, you said it needed to be, the decimal needed to be to the right?
So the decimal needs to be to the right of 1 digit to be in scientific notation. So, small number gives us a, negative power, on 10. Big number gives us a positive power on 10. I'm just trying to give you as many resources as I can. Are we good? Just another minute to write that. And I think I've decided that we're only going to do one section today because I want to give you time for your homework. And also, the next section is fractions, and I want to be able to spend a good amount of time on fractions because I know you're probably fearful of those. You're not going to be at the end, but I'm sure you are now. I'm going to make you love fractions. Well, I'll make you tolerate fractions. Not make you. I can't force that, but I'm going to stop. And that's why I muted myself, just in case I messed up. And I don't want to be talking about the next section in this video.
You having chest pains?
No, I've got a microphone.
Oh, okay.
No, I'm not having chest pains.
Okay.
Not today.
Okay.
That would be really sad on this of all days.
Well, I got some natural listening.
I do not. I'm not spending my birthday in the hospital.
You your birthday today?
Yeah.
Oh, happy birthday!
You're good.
I-
Was it sad?
No.
There's my ADDs around here somewhere too, so.
No, I'm gonna get it.
You wanna do it too? Okay, we got it. We got
Trust
you.
me.
Flaps.
By the time they doing the ambulance come pick him up, take him to the hospital, she's all right.
All right. Speaking of scientific notation. Okay. A large city used 3.25 times 10 to the 7th cubic yards of water in 2019. The city had 1,450,000 residents during that same period. What is the water usage per capita for this city in 2019? What does per capita mean?
How many people? Total people.
No. Per means to divide. Okay. Miles per hour means you take the number of miles and you divide by the number of hours. So in other words, if you drive 70 miles per hour, that means if you've traveled for an hour, you will have traveled how many miles?
You drive
70, right? You use that intuitively when you're in the car, right? You think, okay, if I've got a long distance to go and I can drive this fast the whole time, this is how long it will take me. And that's a really Texan thing to do, just so you know. Per capita means to divide per person. Per person. Capita means head, per head. Per person. So we take 3.25 times 10 to the 7th, and we divide by what? 1.45 times 10 to what power?
6.
To the 6th. Now, you could convert both of these numbers to standard notation and just have numbers. You could convert both of these numbers to scientific notation like we've done here.
Okay, wait a minute.
So that's in cubic yards. This is in people. So how do we do this? Well, what's 3.25 divided by 1.45?
Wait a minute. 3.25. Divide by 1.45.
Mm-hmm.
It's 2.24.
2.24. Okay. Well, that's good news. That means that at least this result has the makings of being in scientific notation, right? How do we know? It's less than 10. It's not always going to happen when you multiply or divide, but it does in this case. Then we can take 10 to the 7th and divide by 10 to the 6th. You mean the exponents?
Yeah.
We don't have that tool in our toolkit. That's true. But 10 to the 7th is 10 million, right? 10 to the 6th is 1 million. 10 million divided by a million is
10 million divided by a million?
uh-huh.
Million. 10 million. What? 10?
10.
Okay.
Just 10. So 10 million divided by 10 to the 6th, which is just 1 million. And if you don't already know this, like just off the top of your head, that's perfectly fine. Plug it into your calculator. 10 to the 7th divided by 10 to the 6th.
I don't.
This is a good time for us to talk about.
Use our calculator.
I will. I will. So,
Oh wait, I got it. Oh, just that one. Wait.
so what you would enter is 10, oops, and then the little up arrow symbol to the 7. You might want to put that in parentheses. Divided by 10, the up arrow 6. And what does that give us?
1,016,000.
10. It's 10
You said divide by 6?
divided by 10 to the 6th.
Okay, 10 to 6.
So you can enter it into your calculator just like this.
You have to show me how to work this, please.
I will. I will. Another way we can think of it is we can cancel out all the zeros, right? And we're left with 10 over 1. Okay, so that's 2.24 times 10 to the 1, and that's cubic yards per person. And don't worry, you're going to get to talk about conversion factors and units for a long time in this semester. What will really help you with these types of problems is practice. And so that is the end of section 1.3, properties and vocabulary for arithmetic calculations. Yes.
Is that our answer?
Yes, the boxed in part is your answer.
So we don't work it. We don't.
You don't what?
Do 2.24 times.
You did better than that. That's the equation. You're solving.
Oh, okay. I'm sorry.
No, that's it. That's in scientific notation, so we're done.
Okay.
Okay.